Okay, so we return to our section in here for the root locus, or in another term, we have two kind of responses in control system. First, steady state. The other thing is a transient, right? We will deal with all the time these two concepts. How can I show that? In this case, this is the t, this is the x and 1, and we can build the system just like this one, and also we can draw the another response in here. Okay, so for a given unit step we have the transient response just like this one, and the other terms the steady state, right? We may have the error steady state in here, or we can adjust the dynamic response of the R system based on these terms. So in the Root Locus techniques, if we want to remove SS error, or ESS is equal to 0, we must choose the K high, okay? And so this yields us to what? The smaller ESS. But just like this one, the overshoot increase and the TS also increase. If we choose the K is smaller and then the high steady state error, just like this one, this black line, right? But low overshoot, right? And low TS in here. So we can satisfy the smaller steady state error, smaller overshoot and smaller TS with using only gain, right? We can't do that. So how can we adjust or change the R system based on this information? So firstly, you must know that we need to change the what? The closed loop poles in order to set these two coefficients in here. Adding with the what? Zeros and the poles, right? And so we call it right now as to what? To derivative term in here. And so this sets to the what? The transient response. And so if we use the integrator just like this one, this is the integral term, it's directly removing ESS, okay? And so if we add any other terms, S plus A or 1 divided S plus B, and then we can change the closed loop poles or the characteristic equation of these terms of this system, and then we can manipulate the what? The transient and the steady state at the both time. But we are using, or if we use the what? The only gain, we can't do that. We cannot reach the whole the poles or the system values in here just like these ones, okay? And so here it comes to the what? To the another topic about the what? The ideal integral compensation design. This is called the PI controller. Proportional integral control. Okay, and so mainly utilized for what? For ESS, steady state error. Okay, but how can we prove that? Firstly, we just assume that we have system like, first of all, we have the RS value for an input in here, and so we can draw the what, the GS, and we must give the K value in here, just like this one, and so the CS, right? And also, if we know that the integral express the what, the steady state error, and then we can draw the another controller form in here, just like this one, the GS, and we can add the compensator in here, K divided by S. Okay, so what is the difference between these two systems in here? First of all, we must draw the root locus, just like this one, sigma and JW. In the root locus, for example, if we have the poles in here, just like this one, okay, and then we may have this kind of K representation in here, okay, see, and so we must take the what, any point in here, just like in the root locus in the MATLAB, and so the percentage error and TS and TR can be set in here. But maybe we need to add the one another pole in here in order to what? In order to adjust the new root locus, because if we have the root in here, just like this one, for example, this is the -2 plus 5j, and so this suppress the whole integral or the steady state error, but we cannot reach it because the selected K cannot compensate the whole of these things in here. And so also we know that if we have the three poles in here, minus theta 1, theta 2 and theta 3 must be satisfied to the what, the 2k plus 1 times 180 degrees, and so this point satisfied. But this cannot, right? We can choose the K, for example 10, and so we can utilize it, but we cannot reach this value, and so we need to change the what, the root locus pole, adding one pole, right? And so this drawing must be rechanged with the what, adding the zeros or the poles. In the integral control, we add the one another pole in here, just like this one. And so if we can do this, we can draw the new root locus. For example, in this case, we have the 4 pole, just like this one, okay? And so we may have the one drawing in here, we may have one drawing in here, but this, for example, A point cannot be reachable in here because it cannot reach at this moment, but this is the desired pole in here. And also we can write that the theta minus 1, 2, this is minus because it's the pole, theta 3 and theta compensator maybe cannot equal to 180 degrees 2k plus 1, okay? This condition may not be satisfied from this condition, and so how can we represent these terms? based on what the different values of the k in here. So instead of using this one, we can adjust the R system. With transient response changed by using the RS plus minus and K S plus A divided by S, and also GS is written in here, the CS, just like this one. And so maybe this representation builds to the root locus into the desired points. Okay. And so we have the 4 poles in here in this system, but also we may have the 0 value. It's coming from the SA, right? Minus A. And so we have the 0 value in here, just like this one. And so desired point may be calculated from the second order approximation, right? And then we can draw these signals in here, just like this one. And so the theta 1, theta compensator 0, this is the theta 0 compensator, this is the theta pole compensator, just like this one. And so I'm sorry, I must redraw these things because it must be clear for you guys. Sigma JW, okay? And so we have one pole coming from the integral term in here, and also we have the 1 0 and also 1 1 1. We have 3 roots or the poles in here, and the A could be a desired point in here, just like this one. Okay. And so we can draw the lines in the root locus. And so this is the theta 1, this is the theta 2, this is the theta 3, and this is the theta 0, closed loop. And this is the theta pole compensator. This is the 0 compensator, this is the pole compensator. And so how can we collect the whole term? Theta minus 1, this is the pole, theta 2 and theta 3, and also theta pole closed loop compensator, and plus ZS can be equalized right now the 180 degrees 2K plus 1. Okay. See, we can use these nominations in here, just like this one. And so we can build the integral controller in here with based on these informations, just like this one. The RS can be built with the minus plus. We can set the K1 controller in here, and also we can give the K2 divided by S controller, the integral controller in here. And so we can plus these 2 nomination, and so the GS and CS can be given in here with the unity feedback signal. And then this is the proportional, this is the integral controller. And so if we add this nomination, and then we can add these conditions in here, just like this one, because this is the error signal, right? R minus C. And so this error signal can be represented in the collection form K1 S plus K2 divided by K1 divided by S. And so the U or the controller input can be calculated this one, because the GS is collection of the K1 plus K2S, and so the GSS is calculated with what? With the simple nominations K1 S plus K2 divided by K1 S. Okay? Do you understand what I'm saying in here? Because in this case we can create the basic nominations in here for the integral controller. Okay, and so just see that this form coming from the proportional plus the integral controller. See, this A is equals to the K2 divided by K1, and this greater K is equals to the K1, and so we can select the parameters in terms of this condition, and so this condition creates the 180-degree condition with the line segmentations in here. This is the integral form of these nominations. Okay? Any question about this? Bilge? Okay. We need to turn into the MATLAB, right? Because we can use it. So this is the MATLAB examples, or you can copy out these things. No. This is the ver1 example. This is the ver2, week 6, 7, and PI. Okay, M script X, and then can delete the terms just like this one, and so the PI controller design. Okay, so but for root locus, in order to understand how we can change the PI controller, first of all we define the normal proportional controller. Zeros P is equals to this one, and poles P, for example, -1, -2, and -10. We have these roots at the poles, and gain P can be assigned with the 1. Okay, and so GP can be created with the ZPK, 0 pole K command in the MATLAB. Zeros P, poles P, and gain P. Okay, and so if I run this code, and then we will have 1 divided by S plus 1, S plus 2, S plus 10. Okay, this is the definition of the R transfer function. This is the open loop transfer function, right? So also we can define the PI design in here. For this design, zeros PI is equals to the for example, minus 0.1. This is what? This is A, right? This is A. S plus 0.1. And so the poles PI is equals to the 2. We must add the 0, -1, -2, and -10, right? These are the pole. And gain PI is equals to 1. Okay? So we should write the PI, but This is the greater, must be greater in here, and greater zeros p, pulse p, and gain p, and pi, and gain pi. Okay, so first of all, we have two transfer function in here, okay, but with the different conditions. Firstly, just see that the GP 1 divided by s plus 1, s plus 2, s plus 10, but the integrator term or the integral controller can be added with the what with s plus 0.1 and s plus 1, s plus 2, and s plus 10. We can do that. We can add the what the PI controller in here. And so, how can change these nominations or the organizations in the what in the root locus domain? First of all, just remember that we need to give the desired what the overshoot. For example, PO percentage overshoot 55 100, and zeta can be calculated with what the SQRT, the log PO over square divided by pi over square log PO square. Okay, this is the zeta line, and so we can use the what the root locus of P in here, just like this one. This must be equals to the what the GP. Okay, but we should use the subplot in here 1 2 1. Okay, and grid on should not be used. Grid s grid zeta these terms, and also we should give the 2, and the PI must be given in here. Okay, at this case, at 2 case, we should write the what the zeta. Okay, and so if I run this code, we have the 2 root locus, but see that these 2 root locus are different from each other, right? This root locus have this one, and this have this one. We have 1 0 and the what integral term, which is removed to each other in here, but the root locus of PI is changed with the P1. See that? And so how can we affect these results? 0.187 is accomplished with the what? With the values of the 153 for the what? For the 55% overshoot. But in the PI root locus we have different results. 153, but the overshoot 56.1. Okay, and so just see that the frequency and the overshoot and the damping ratio and the pole locations are what are closing to each other. But what is the difference between these two systems in here? The root locus is changed, but the gain is same in these 2 cases, right? And so in order to find the exact values of this one, the gain is 149, and the the gain of the P is the what must be selected 155, but the GPI must be selected to 149. This time we have difference to 6, right? And so, but this is the important difference in here. Just remember that. How can I prove that? We must choose the root locus of P for the what? For the 55% overshoot as the what? 155 for the P. But the PI should be selected as the 149 for the overshoot of the 55.1. Okay, and so we must write the selected p-value as the 155 and selected k pi must be chosen the 149. This difference of the coefficients coming from the what the integrator effect on the system. Okay, how we can compare our results? CLTF pi can be calculated with what the selected KP and times GP 1 and also PI and PI, right? And so figure step response CLTF P, hold on, and step response CLTF PI, and title the step response, and grid on must be open in here, and so the legend of the pi P and PI. Okay, and so if I run this code, what is the difference between the closed loop response? See that this is the pole location of these times, and so we have different gain in here with small deviation, but we have different gain. But if we have this condition, the red line is the PI controller, is the blue line is the what the only P controller. What is the difference between these two signals? Bilge, just answer that. Yes, Bilge. The one of them is the integral plus P, but you must examine or evaluate the step response. What is the difference of the two response in here? Yes, we don't have any steady state error in here, just like this one. If we choose the steady state values of these terms, and so the only proportional control creates the what? The 0.88 value for a unit step. We have the steady state error, but in the PI system, the final value is the 1, which means that this final value going to what? The unit step response, which means that the steady state error is 0 at the final time, right? And so the integral controller design suppress the steady state error, right? But also we need to examine the peak response in here, the peak response of the peak deviation 63.8, and the other term is the 51.8, right? What is the difference between these two terms? The only P controller creates the what? The 50 overshoot, but the other term is creating overshoot with the what? The 63. What is the reason between these two difference, Bilge? I have told you in the previous lesson. Can anyone answer that? In the integral controller, we reached what? Yes, case selection is important parameters, but we have another source of problem in here because CLTF P is equals to the what? These terms. This is the third order equation. Not the PI is to what? Is to what? 1, 2, and 4, right? We have, in the closed Bressner function, we have the third order response. Yes, yes. This one is the third order, and this one is the what? This is the third order, this is the fourth order, right? And so third order can closing to response of the what in these terms. Just see that 50 overshoot. We may reach him, but in the fourth order we have the different overshoot ratio. The difference is greater than the previous one. Bilge. See that? Just remember that this is important. If you want to design the higher order system, you cannot easily select the overshoot, steady state error, or the setting time parameters. But if we are using the integral controller, we don't have any steady state error at the what? At the final time, right? So this is the integral controller. Based on the what? Based on the root locus tables. For example, if you want to design another system in here, just like this one, if you want to analyze the scores of the what? The 0.5 in here, for example, minus 0.5. And so if you run this code, and then we will have the what? The zeros. It's far from the zero values, right? And so our result is different in here, but the characteristics of the system steady state is same. Final value is the 1, right? But the final value is the 0.68. But if you change your system, you must choose the what? The new p-values at each time. See, if we have these nominations in here, and also just see that. And now we have the 155, and at now see, in the PI controller we must choose the gain as equals to the what? The 124, right? And so in this case we must update the P controller just like this one. And so if I rerun this code with this parameter, and then see that the characteristics of the equation is the what? 45, and the characteristics of the equation is same with the previous one, right? And so we can easily analyze the R effect based on the what? The root locus analysis in here, just like this one, okay? And also maybe we can change the poles of the system just like this one, for example 20 and 20 and 1, and so this is the different system. It's coming from what? Another response of the R system. And so if the system is changed, and so our proportional term also changed in here, right? Because the R response, just like this one, the PI is closing to what? The 1, because the steady state error suppressed from the system. That the P is constant values. But in this case we must examine the R system in here for the intersection point of the what? The 0.180 in here, and so we must choose the gain in here 459 and also 439, and see 459, 439. This is the proportional coefficients. This is the PI coefficients in here. And so if I rerun this code and then see, if the system is changed, the characteristics are the same. if we are using the what? The proportional integral controller. See that if the system is changed and then we have the same characteristics at the what? At the output signal. And so if we are using the root locus techniques, and then we can set and we can find the proper coefficients of the what in this system based on these informations. Okay? And so just see that this pi coefficients is equals to the what? Is equals to the k1. Okay? And so the k1 must be equals to this one. What is the k2? Bilge, how can we compute this k2? No, because the 439 is equals to the k1. Just like this one, is proportional coefficients. But see that if we have using the 0.1 values in here, and so we have the s plus 0.1, which means that the selected kpi is equals to the k1, but k2 divided by k1 must be equals to the what? The 0.1. Right? Because this is the coefficients of these terms, right? And so this is calculated with the what? The k2 is equals to the what? This is equals to the a, and so 0.1 times k1. Did you understand that? Because in this case we have, just see that, s plus 0.1, right? And so the selected k is coming from the what? The root locus, and then this must be equals to the what? To the k1. And so k2 divided by k1 must be equals to the what? The 0.1. And so this is 0.1 times k1 must be equals to k2. And so in order to design your system, k2 must be selected with the 0.1 k1, and the k1 must be equals to what? The selected kpi. Okay? You get that? Okay. So